So, in this unit, we are going to be looking at basically, we will come back to things that we've seen before, like density, but we'll introduce new terms like pressure. We'll learn about buoyancy in a liquid, what buoyancy is, the Archimedes Principle, and the pressure in a gas. We'll learn about atmospheric pressure. We'll learn about Pascal's principle, buoyancy in a gas, and all of that. Okay, so let's start with density. What is density from what you've learned from a previous unit like Unit 1? If you remember, we said density is an important property of materials like solids, liquids, gases, they all have density. It is actually the measure of the compactness or how much matter we have in a specific volume, how much mass an object occupies, the lightness or heaviness of a material. All of that is density. Okay. How do we calculate density? Density is equal to mass divided by volume. So if we want to know the density of a substance, we take the mass, we divide it by the volume. And units of density, in order to obtain the unit for density, what we do is we take the unit of mass and we divide it by the unit of volume. The unit of mass is the kilogram or the gram, and units for volume is either the centimeter or the meter cube. Centimeter cube or meter cube. And so remember, the kilogram goes with the meter cube. So the unit of density will either be kilogram per meter cube or grams per centimeter cube. You can't mix them. Okay. Sorry. The density of mercury is 13.6 grams per centimeter cube. So what that means, in every 1 gram of mercury, in every 1 centimeter of mercury, there is 13.6 grams. So if you compare the density of mercury to that of water, you realize that mercury has 13.6 times as much mass as an equal volume of water. There's another terminology that we call weight density. And in this case, instead of using the mass, we'll use the weight. So the weight density is the weight divided by the volume. And we often express that in pounds per cubic foot. So the density of salt water is 64 pounds per cubic foot. More dense than fresh water. If you look at fresh water, the density is 62.4 pounds per cubic foot. All right, let's check this out. Which of these has the greatest density? 100 kilogram of lead, 100 kilogram of water. Both are the same. None of the above. Think about it. They have the same mass and weight, but different volumes. Any amount of lead is more dense than any amount of water. Okay? Metals are usually more dense. Water is like it has a density of 1 gram per centimeter cube or 1000 kilogram per meter cube. So metals generally have a higher density than water. So now let's look at pressure. What is pressure? What we call pressure is the force acting per unit area. So pressure is defined as force per unit area that one object exerts on another. And so the formula for pressure is force divided by area. So pressure depends on area over which force is distributed. And units of pressure include the pound per square feet or square foot, Newton per meter square, or the Pascal. By the SI unit of pressure is the Pascal. You can take this example. You take your pen or your pencil, right? And you take the sharp end and you try to press that your against the surface of your palm, your hand. When you press using the very sharp end, you realize that you feel so much pain. Why? Because the pressure is very high when a force acts on a very small surface area. Now what you're going to do now is you take now the other end of the pencil. So instead of the sharp end, turn your pencil and you try to press it using the surface that's a little bit larger where you have the eraser, the gum. And you realize that you feel less force, you feel less pain. Why? Because the surface area is bigger. The surface area in contact with your palm is bigger than the sharp end. So why try this example? Because pressure is actually extremely high when a force acts on a small surface, and this pressure is going to drop when the force acts on a larger surface. So pressure in a liquid. So in a solid, it's easier to say pressure is force per unit area, right? That same logic applies for liquid. Force per unit area that a liquid exerts on something. So pressure in a liquid is depth dependent. So if you have a liquid, let's say in a certain container, right? What do we mean by is depth dependent? What we mean here is the pressure at the bottom of the container is much higher than the pressure at the surface. So what we say here is that pressure increases with depth. So the deeper you go into water, the higher the pressure. Right? The deeper you go into water, the higher the pressure. So for example, swim twice as deep and the pressure due to the weight of water above you is twice as much. So if you're swimming and you're going right below the water, deep down the water, you will experience more pressure than someone that's closer to the surface. Because for you to obtain the total pressure, you need to add this to the atmospheric pressure acting on the water surface. So the pressure due to the water plus the atmospheric pressure. And we are going to learn what atmospheric pressure is very soon. So effects of water pressure. So pressure in liquids, you see, acts perpendicular to surfaces of a container. Perpendicular means a right angle. Perpendicular means a right angle. So liquid spurt at right angles from a hole in a surface curving downward. The greater depth, the greater the exceeding speed. So if you try this, a container with so many holes, you will realize that the greatest pressure is going to be from the hole that is really down, because the more you go in depth into the water, or the deeper you go into the water, the higher the pressure. Okay, so pressure increases with depth. So the water coming from this hole is going to actually cover a higher distance. Okay, it will go further than all the other ones. It will go further than all the other ones.
Is that Poppy Abroda too? Poppy 2 or Poppy?
So
Sorry, which
can
daddy did you want to call? I'm seeing 3 contacts with that name. Poppy Abroda.
pressure in a liquid. Pressure in a liquid, it acts in all directions. So that's another characteristic of pressure in a liquid. It acts in all directions. Examples: your ears feel the same amount of pressure underwater no matter how deep you tip your head. Bottom of a boat is pushed upward by water pressure. Pressure acts upward when pushing a beach ball underwater. Those are characteristics of pressure in a liquid, independent of shape of a container. So the pressure in a liquid doesn't matter. It does not matter on the shape of the container. And I want you to observe this picture right here. These are tubes of various shapes. If you look at them, look at this one, this one, this one, this one. Okay. When you put liquids in there, what you will realize is that all these liquids, they have the same level. They all will end up having the same level no matter the shape of the various tubes. Why? Because that is to confirm that pressure is independent of the shape of the container. All these tubes will experience the same pressure provided it's the same liquid. So liquid pressure is calculated as weight density times depth or times height. Weight density times height. So the water tower, force of gravity acting on the water in the tall tower produces pressure in pipes below that supplies many homes with reliable water pressure. Okay. So if this is a water tank, the highest pressure is going to be felt at the bottom. Okay. Check for understanding. Suppose water from a tall tower supplies a nearby home. If water faucet upstairs and downstairs are turned fully on, will more water per second flow from the downstairs or the upstairs faucet? Or will water flow in each be the same? Okay, if you remember, we're talking about pressure increasing with depth. So downstairs is at a lower depth, it's at a higher depth than upstairs. So downstairs water pressure depends on the depth below the free surface. Downstairs faucets are simply deeper and receive a greater pressure, and therefore will have a greater rate of water flow. Does a 3-meter deep lake or a 6-meter deep small pond exert more pressure on a dam? Again, everything depends on height. Okay, a 6-meter deep small pond will exert more pressure on a dam because the, the depth is 6 meter compared to 3 meter on the lake. Buoyancy in a liquid. What is buoyancy? You see, sometimes when you're swimming in a pool, I don't know if you've ever experienced that you feel like you're light. When you're in a pool, you feel like your weight is kind of less than your normal weight when you're outside the pool. So, what we call buoyancy is the apparent loss of weight of any substance that is submerged in water or that is partially or totally immersed in water. Okay, so when you put, let's say, a stone in water, this stone is going to experience an apparent loss of weight. And so when what you realize is when you go into a pool, if you monitor it, you realize that the liquid of water, I mean, the level of water is going to rise. Okay, it will rise. If you put a stone into water, yes, the level is going to rise. Okay, and so what happens is you experience an apparent loss of weight that is equal in amount to the weight of the water that you display. So let's say if you dive into a pool, you see the water rising, you will experience an apparent loss of weight equal to the weight of the water that you displayed when you dived in. And that is what we call buoyancy. Okay, that is what we call buoyancy. So the apparent loss of weight of a submerged object. And so that loss of weight, remember, is always equal to the weight of the water or that the object displays. So Archimedes' principle goes in the same direction with buoyancy. This was a discovery from a Greek scientist called Archimedes, and today the principle is named after him. So what he did is that he related buoyancy to the displaced liquid, which is what I just explained. And so what Archimedes' principle states is that an immense body, whether completely or partially, is buoyed up by a force equal to the weight of the fluid it displaces. So if you put a stone or if you put, let's say, any object in water, so long as this object is partially, that means it's not completely covered by water, or is completely covered by water, as soon as it touches water, you will see the level of the water is going to rise. So that difference in level is what we call the water that is being displayed. Okay, so Archimedes' principle states that when you put any object in water, including yourself, when you dive into a pool, you will experience an upward force, right? And that upward force is what we call that buoyancy. So that upward force is going to be equal to the weight of the water that you displayed when you dived in. And so buoyancy also applies to gases and to liquids. So apparent weight of a submerged object, how do we calculate that? How do we calculate that? The weight out of water minus the buoyant force. So take an example. If you have a 3 kilogram block that's submerged in water, it will apparently weighs 1 kilogram. Then the buoyant force or weight of water displayed is 2 kilograms. So the buoyant force is the weight out of water minus the apparent weight. So 3 kilogram minus 1 kilogram. That's the buoyant force. So with Archimedes principle, there's what we call a displacement rule. A completely submerged object always displaces a volume of water equal to its own volume. Okay? So if you put a stone here into a water that was full, you realize that as soon as you put that stone, you can collect the water that is going to flow into a different container. Okay? So that water that you collect is actually the water that is being displayed. So if you take the weight of this water displayed, okay, you will realize that that is the upward force that this stone is going to experience. So you place a stone in a container that is brim full of water, and the amount of water overflows equal the volume of the stone. Buoyant force is equal to the weight of the fluid displayed. It can also be understood by pressure differences. The greater pressure against the bottom of the box minus the pressure on the top result in an upward force, the buoyant force. Buoyant force is equal to the weight of the fluid displayed. We cannot repeat that enough. Okay, we need to understand that those differences. The greater pressure against the box, pressure on the top of the box. On which of these blocks submerged in water is the buoyant force the greatest? 1 kilogram of lead, 1 kilogram of aluminum, 1 kilogram of uranium. So what we'll say here is the block that has a bigger volume, okay, because the largest block is the aluminum one. It displaces more water and therefore experiences the greatest buoyant force. So which one will displace more water will experience more force? Okay. Still talking about Archimedes principle, we'll talk about flotation. So there's a principle of flotation. A floating object displaces a weight of fluid equal to its own weight. Example, if you have a solid iron 1 ton block may display may displace 1/8 ton of water and sink. The same 1 ton of iron in a bowl shape displaces a greater volume of water. The greater buoyant force allows it to float. Okay? The reason a person finds it easier to float in salt water compared with fresh water is that in salt water, a smaller volume of water is displaced. A floating person has the same buoyant force, whatever the density of water. A person floats higher because a smaller volume of the denser salt water is displaced. On a boat ride, the skipper gives you a life preserver filled with lead pellets. When he sees the skeptical look on your face, he states that you will experience a greater buoyant force if you fall overboard than your friends who wear styrofoam filled preservers. He's correct. Okay, he's correct, but what he doesn't tell you is you will drown. Your life preserver will submerge and displace more water than those of your friends who float at the surface. Although the buoyant force on you will be greater, the net force, although the buoyant force on you will be greater, the net force downward is still is greater still. Okay, so you will drown. So it's better to get a styrofoam than a life preserver filled with lead pellet. Okay. All right. We will talk about pressure in a gas in our next lesson.